So I went really long last week, which means I'm a bit of a penalty box. I'm going to try to keep things pretty brisk today, which is good because it's going to be mostly a conceptual lecture rather than an analytical one, at least in terms of my goals for what you'll get out of this. But before I get on to the clappy introduction, here's a question for you. Just how would you microfound, how would you encode a penalty box? Hey everybody, welcome to PS231. So in the previous couple lectures, we've talked about how to add time to our book of fables. We talked about extensive form games, and then we talked about how to analyze them to find subgame perfect equilibria. In particular, because we were looking at games with a finite time horizon, you knew when the last day was, that finite time horizon gave us an opportunity to use an intuitive algorithm called backward induction, or a generalized flavor where we just go to all the last subgames and then work backwards. Either way, we just sort of went to the end of time, whether it's one person's decision or many, solved it, and then went back to the beginning of time as we needed to. And that's a perfectly good way to proceed, and probably if you're going to get anything out of this class, which is a pretty big if, but if you're going to get something out of this class, chances are very good that it'll be something like you can draw a finite horizon tree. You can think through who gets to move when, and what the end of time is, and what the utilities would be, and then you can just use backward induction. That's a nice way to think about all sorts of interactions that are political, or maybe even just decisions between you and your friends. Now, that last day approach works very well in interactions where you know that there will be a last day and it's publicly known. So for example, we're in a 15-week class together. You know when the last day of class is, and you're very excited about it. You know when the day of the final exam is, you're less excited about that. But we know when the last day of our interaction in this class will be. If you intended to do some grade grubbing, which don't you dare, but if you intended to do some grade grubbing, you know that you would have to do it before the day that grades are due. Right? You know when the last day is, and so you can work backwards from there. And in a larger sense, you know when you're going to be graduating from the U of I, and so you can think about where you would like to be at that particular last day. You would like to know what skills and other bona fides you have on graduation day, and then you can just work backwards from there. Oftentimes you have some goal, there'll be some time that you have in mind, and you can take that time and work backwards. But not everything works that way. So for example, if two countries are in some bargaining process with one another, it isn't obvious that there's some last day of the semester for them. Right? The countries don't die very often. That's an interesting truism. And sometimes they might try to impose some deadline on themselves to say, okay, we're going to handle all of our negotiations and they will be signed by December 31st. But if they're the ones setting the deadline, there's no reason to believe that deadline necessarily. You can run right through that deadline and keep haggling on January 1st if you want to. In other words, there isn't necessarily a last day for interactions under anarchy. Or even in the context of the state, many interactions are sufficiently informal between players who see one another pretty often that there isn't a last day to start there and work backwards. So even though our concept of subgame perfection, our notion of credibility is important, it seems like we've got a modeling shortcoming in the sense that we haven't talked about infinite horizon interactions where we don't actually think that the people are actually going to live forever. We don't actually think that like entropy will eventually take us to some final day, capital F, capital D. We're modeling an infinite time horizon not because we think that time is actually infinite, but rather because we don't know when the last day is. We can't say there's a final time period, which means we have to move on to infinite time. So our models haven't allowed for that, and certainly our backward induction algorithm, which relies on terminal nodes being solved so that we know which decision nodes are, in a sense, late in the interaction. Well, if we have an infinite time horizon, what the hell does late mean? There's such a thing as later. Some things might happen later than others, but late, in terms of with respect to the last day, if there's no last day, what the hell does late mean? So these shortcomings on the modeling and the analytics side Not only are they shortcomings in terms of me just stating them to you, but they also seem to be substantively rich. There are many interactions where we would think that the possibility of cooperation in the future, or you worrying about what people will do conditional on what you did today, maybe you won't do things that are short-term best for you today because you're worried about what will happen to you tomorrow. Maybe you won't commit a crime today because you're worried about punishment in the future. Maybe you won't tattle on your fellow suspect today because you're worried about what they'll do to you in the future. And certainly criminals don't very often say, and the Constitution for our particular organization says that what we have to do is handle all of our business by December 31st. Although, there's an awful lot of infrastructure involved with many criminal organizations, and many of them serve basically as states or firms. So I don't want to cast too much of a disparaging eye in an economic sense. Don't commit crimes. Because I'm in the penalty box, which means that I'm under self-imposed exile because I'm worried that you'll get really mad at me at the future if all of my lectures continue to be an hour and a half. Because I'm in that penalty box, I don't want to talk too much more about what you can expect in the future. I don't want to talk too much about what you've already done in the past, which is very notable. Instead, I just want to tell you to get yourself some liquids, to get yourself comfortable, to get yourself locked in, because there's going to be some really beautiful concepts to show you along the way today. So let's get to it. In the A block, I want to frame the problem by showing you what would happen if we played the prisoner's dilemma multiple times, but a finite number of times. We'll see that that story has a predictably tragic ending, and that will motivate us to talk about what an infinite time horizon might look like. We'll use that opportunity to talk about what it would mean to be patient. What does it mean to weigh the future, finite or otherwise, a little bit less than you weigh today? What would happen if Udals today mean more to you than Udals tomorrow? What would happen if an IOU for $100 wasn't worth the same as $100 to you? Then over in the B block, I'll show you some equilibrium analysis that emerges when we study the prisoner's dilemma repeated an infinite number of times. What happens if there isn't a last day for us to defect on one another? What happens if the tragedy that kind of causes all the other tragedies, the root tragedy, what happens if the root tragedy doesn't have a chance to happen? Can we incentivize cooperation? Can we wind up getting ourselves out of the tragic outcome that emerges in the prisoner's dilemma if we're worried about an infinite time horizon of prisoner's dilemma auta? Oh my God, that's heavy when you think about it. It's going to be even heavier once you see it, I assure you. Then in the C block, I'll show you that actually repeating the prisoner's dilemma an infinite number of times, or indeed any game an infinite number of times, provides us with a very large set of institutional opportunities. I'll show you what's called the folk theorem of infinitely repeated games in the context of the infinitely repeated prisoner's dilemma. I'll show you that in the context of the prisoner's dilemma, there are some good outcomes that could happen, there are some bad outcomes that could happen, and there's an awful lot of outcomes that could happen in between. In other words, we have all sorts of opportunities for clever players to take advantage, or for well-intentioned institution builders to try to generate good outcomes. Regardless, this is a much happier set of stories than what we talked about in the original Prisoner's Dilemma, which was very, very sad. You know, this is one of those lectures that it's going to be really tricky, and there's going to be some formulas, and there's going to be some things that happen along the way that are a little bit of magic fairy dust, and I just ask you to trust me. I'm not going to be asking you too much in terms of the analytics of this. I'm not going to be asking you to solve an awful lot of infinitely repeated games. I'm not going to be doing that to you. This won't be on the final. You don't have to ask me. It won't be on the final. Because of that, I hope you can just enjoy the movie a little bit and just let these concepts wash over you, because you have an awful lot of future to look forward to, and it'll be nice if you had a sense about how to navigate your way through that future, whether it's a nasty one like the Prisoner's Dilemma, or hopefully something a little bit happier. However, in the immediate short term, your future is a lot less happy than it would be, because you got a lot of lecture to sit through. So let's get started. The A block, I just want to provide some basic motivations for our enterprise today. So step one is I want to revisit our good friend, the Prisoner's Dilemma. Wait, why is it our good friend? This is a sad story. So you remember the Prisoner's Dilemma is one of the most famous games, if not the most famous games in all of game theory, and it's famous because it has a predictably tragic ending. So the basic idea is you'll remember that there's two suspects who have been into separate interrogation chambers where they're given some strong incentives to tattle on one another. So these detectives that put them into these separate interrogation chambers basically say to them something to the effect of, if neither of you tattles, we can just get you both for a misdemeanor and you owe us a fine. If both of you tattle, then you both go to jail for a long amount of time. And if one of you tattles and the other one doesn't, then the tattler goes home free, and the person who got tattled on is in jail for the rest of their life. So I'm a suspect, you're a suspect, we are two suspects. I'm the row suspect, you're the column suspect. I'll be suspect 1 throughout and you'll be suspect 2. Or countries that are thinking about making arming decisions, or people that are thinking about public good provisions, or shepherds that are thinking about not overusing a resource. A million things are like prisoner's dilemmas. I actually think the plural is dilemmata. But let's not be that pretentious today, huh? Can we wind up getting ourselves out of the tragic outcome that emerges in the prisoner's dilemma if we're worried about an infinite time horizon of prisoner's dilemma-ata, prisoner's dilemma-ata, prisoner's dilemma-ata, prisoner's dilemma-ata, prisoner's dilemma-ata? Oh my God, that's heavy when you think about it. Okay, so I'm the row suspect. I'm going to use slightly different words here just to make my life easier throughout the day's notation. So I can either cooperate by staying silent, or I can defect by tattling. And you can either cooperate by staying silent, or you can defect by tattling. I'm going to take all of the utility numbers, and again, for reasons of convenience, I'm going to subtract 2 from them all, based on from the prisoner's dilemma that you've seen before, and this will make the math quite a bit easier throughout today's lecture. So if we both cooperate, that'll be 1 happiness point apiece. If we both defect, it'll be 0 happiness points apiece. If one of us cooperates and the other defects, then the defector gets 2 happiness points for being at home free for the rest of their life, or at least until they commit another crime. And the one that got defected on will have -1 happiness points for being in jail for the rest of their life. So in other words, it's like 1, 1, -1, 2, 2, -1, and 0, 0. You'll notice, per usual, that the cooperate outcome, Pareto dominates the defect outcome. Both parties do strictly better if they both cooperate. And yet the sad story that we've seen about the prisoner's dilemma up to this point is that the unique Nash equilibrium is that both of the suspects defect. They both tattle. So in other words, the unique Nash equilibrium is Pareto dominated by another strategy profile. And that's very sad. That's a sad outcome. It's been the subject of an awful lot of philosophy, political philosophy, and other kinds of philosophy actually, and all sorts of theorizing across the disciplines where the prisoner's dilemma is applicable. How do we generate cooperation? What could we do to land on cooperate instead of on defect? As of right now, the collective action problem baked into the prisoner's dilemma is precluding us from enjoying the benefits of mutual cooperation. Now, in Nash Equilibrium Week, I said, well, maybe the state can provide carrots and sticks. Maybe the state can punish defectors or incentivize cooperators. Maybe the state can shift incentives. But many informal interactions, or interactions between states under international anarchy, don't feature a state that can help us to do that. So the question is there a way for us to incentivize mutual cooperation in the absence of a state to shift these incentives? And that's the subject of today's lecture. Chewy is really saying hi. So here's a question. Suppose that we tried to incentivize cooperation by thinking about playing the prisoner's dilemma twice. In other words, suppose that there were 2 time periods, time period 0 and time period 1. And maybe what will happen is that if we think about what will happen down in time period 1, maybe we can get good behavior in time period 0. Heck, if we're being greedy, maybe we can get cooperation in both time periods. So let's think about what would happen if we played the prisoner's dilemma twice, adding up our utilities, and where we can observe what we did in time period 0 as we condition what we do in time period 1. Maybe I could say to you something like, well, if I observe that we both cooperated in time period 0, then in time period 1, I will reward you by cooperating yet again. Maybe I can offer you something where I'm like, if we observe what we did at the beginning of time, then when we get to the end of time, we'll have learned enough about one another to see that we're playing some kind of cooperative strategy. Maybe we can generate some happiness just by allowing a number of repetitions. Maybe we can just repeat the game, and that generates cooperation. So let's think about what that would look like in a game tree. Remember, we can do sort of simultaneous games embedded in a time structure if we're clever with information sets. So what we're going to do is we're going to envision a big, haul-ass, repeated prisoner's dilemma where it's two interactions. We'll have strategic time go from north to south. And broadly speaking, you can think about time period 0 being what happens up here in the top half, and time period 1 being what happens down here in the bottom half. We'll be playing the prisoner's dilemma twice, once in time period 0 and once in time period 1. You'll see why I'm starting from 0 in the second block, okay? It'll just make all of the math easier. Just keep trusting me today. And you're like, trusting me hasn't served me very well the last 10 weeks. Shut up, it served you so well. So, in time period 1, at the beginning of time, player 1 can either cooperate or defect. And player 2 can either cooperate or defect. Player 2 won't be able to observe what player 1 does in time period 0. It's going to be a simultaneous move game here in time period 0. And so I'll use an information set to link player 2's two decision nodes. That yields 4 possible outcomes in time period 0. It could be that we both cooperated. It could be that I cooperated and you defected. It could be that I defected and you cooperated. Or it could be that we both defected. Okay? So there's 4 possible things that could happen in time period 0 if we're focusing just on pure strategies, which we will today. And what I'm saying is, we're all going to observe what happens up here in time period 0, and then we'll have a chance to play another prisoner's dilemma here in time period 1. So in other words, after cooperate, player 1 can make a move. They can either cooperate or defect. And player 2 gets to make a move. They can either cooperate or defect. And there's an information set there to say that player 2 gets to observe what happened up in time period 0, but they don't get to see what player 1 does in time period 1. It'll be a simultaneous move up here and a simultaneous move down here, but where what happens down here gets to observe what happened up here. The same goes for the other 3 histories that could happen in time period 0. After cooperate defect, player 1 gets to make a move, they can cooperate or defect, and player 2 gets to make a move, they can cooperate or defect, and they don't get to see what player 1 does in time period 1. And the same for the other 2 histories. So you'll notice now we have this gigantic game where we play one prisoner's dilemma up in time period 0, and then there are 4 possible prisoner's dilemmas depending on what we see happen in time period 0. And you'll notice that player 1 gets to see what happened. There are no information sets here, right? There's no linkages. Player 1 gets to see what happened in time period 0, and so does player 2. Player 2 doesn't know what player 1 did in time period 1, but they get to see everything that happened up in time period 0. I feel like I'm making this way more opaque than it needs to be, per usual. And the idea here is that the utilities that we'll put on each of these 16 terminal nodes will be what happened in time period 0 plus what happened in time period 1. So for example, if we both cooperate in time period 0 and we both cooperate in time period 1, then we get the 1 happiness point for mutual cooperation in time period 0, plus the 1 happiness point for mutual cooperation in time period 1, so 2 happiness points apiece. Just to choose a random one, if I defect and you cooperate in time period 0, so that I get 2 and you get -1 in time period 0, and then in time period 1, you defect and I cooperate, then we wind up with 2 plus -1 for me, which is just 1, and -1 plus 2 for you, which is just 1. That's 1, 1. So what I'm going to do is I'm going to fill in all 16 of these terminal nodes with their respective utility numbers. You can pause the video if you need to and check to see that in every case, it's just the sum of what happened in time period 0 plus what happened in time period 1. We'll be seeing these numbers in a matrix here in a second, so you'll have a chance to review them all. And you're like, oh, now I can sleep at night. Now you can sleep at night. Now, here's a question. If I wanted to find the subgame perfect equilibria, then what I need to do is I need to identify every subgame, find the Nash behavior there, and then think about the whole enchilada, which is itself a subgame, right? So look at this game, pause the video, and figure out how many subgames there are. Remember, a subgame is a part of the game that begins from a unique decision node, ends only in terminal nodes, and doesn't tear information sets apart. So how many times does that happen in this game? And as a hint, the entire game is itself a subgame. Are there any others? Pause the video. Welcome back. There are 5 subgames. Each of the time period 1 games is itself a subgame as well. Okay? So what we need to do is we need to convert each of these to their matrix forms, find the Nash equilibria there, and then figure out how those utilities would act on the time period 0 prisoner's dilemma once we've added the equilibrium utilities from time period 1 to time period 0. It sounds bad, but it's actually not that bad. So the first thing I want to hone in on the version of the game where we both cooperated in time period 0. So if we both cooperated in time period 0, we find ourselves in this subgame, which I'll represent as a matrix now. I'm row player and you're column player. If we both cooperate, then it's the 1 happiness point that we got from mutual cooperation in time period 0, plus the 1 happiness point we each get from mutual cooperation in time period 1. That's 2. If I defect and you cooperate, 3 for me, right? 1 plus 2, and 0 for you, 1 plus minus 1. Same works in reverse if I cooperate and you defect, 0 for me and 3 for you. And if we both defect, 1, 1. What are the Nash equilibria of this game? Ah, crap, it's mutual defection. So if we both cooperated in time period 0, then the only Nash thing for us to do in time period 1 is to both defect. That doesn't bode well. Let's keep plowing through these subgames though. Let's go to the version of the game where I cooperated in time period 0 and you defected, you jerk. So that subgame looks like this. You can check those utilities if you want to. Draw in some stars to figure out what the Nash equilibria of this game are. Ah, crap, it happened again. We both defect again. All right, let's go to the version of the game where I defected and you cooperated. And let's see what happens. That version of the game looks like this. We both defect again! Let's just do the inevitable thing and let's check the version of the subgame where we both defected in time period 0. That looks like this. Find the Nash equilibria. We both defect again! So in other words, if we both cooperated in time period 0, we'll both defect in time period 1. If I cooperated and you defected in time period 0, we both defect in time period 1. If I defected and you cooperated in time period 0, we both defect in time period 1. And if we both defect in time period 0, we both defect in time period 1. It doesn't matter what we did in time period 0, we both defect on the last day. So in other words, we can just trace the DD in every one of the games that happens in time period 1. Every time period 1 game, you can just trace the DD. So now, when we go to the top of the game, we already know what will happen in time period 1, which is mutual defection. So what you can do is you can just add the 0 from time period 1, no matter what happens, to the payoffs from time period 0. In other words, if we both cooperate in time period 0, then we'll both defect, and we'll wind up with 1 happiness point apiece from today. If I cooperate and you defect, then that'll be minus 1 happiness points for me, plus 0, and 2 happiness points for you, plus 0. That's just minus 1, 2. Same works in reverse if I defect and you cooperate, 2 minus 1. And if we both defect, we get 0 happiness points today, and we'll both defect tomorrow and get 0 happiness then, we'll get 0 happiness points. In other words, we have not modified our prisoner's dilemma 1 iota. And that means there's going to be mutual defection in time period 0. So, in order to get the subgame perfect equilibrium right, we have to think about what happens in all 5 subgames. In time period 0, we both defect. In time period 1, had we both cooperated, we'd both defect. In time period 1, had I cooperated and you defected, we'd both defect. In time period 1, if I defected and you cooperated, we'd both defect. And in time period 1, if we both defected, we'd both defect. So the only thing that happens in this game is defection everywhere. Defection, 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 defection. That's sad, that's sad, that's sad. Now it's almost like we're rubbing it in. Right? As if mutual defection wasn't bad enough in a one-shot version. And I got news for you. If we repeat this game any finite number of times, it could be that we play this game every second of every minute of every hour of every day of every week of every month for a year. But so long as we knew what would happen on the last second of the last minute of the last hour of the last day of the last week of the last month of that year, we were both defected that game. Once we got to the end, we would both defect. And that would kind of create this ripple effect of sadness, and we would defect every second of every minute of every hour of every day of every week of every month of that whole year. We would just defect and defect and defect and defect and dot 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 and then defect at the end. And we'd get a steady stream of zeros. And we wind up with 0 happiness points. If you repeat the prisoner's dilemma any finite number of times, the unique subgame perfect equilibrium is for us to defect in every subgame. If you know when the last day is, which is to say, if you know when that last little bit of nasty is going to happen, then you would be nasty the day before that day. And if you knew that, then you'd be nasty the day before that. And if you knew that, you'd be nasty the day before that. Dot, 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 and you'd be nasty on the first day. You'd be all sorts of different kinds of nasty. So that's kind of sad. That's kind of sad. Finite repetition doesn't get you where you need to go. In the lab, it does, actually. It's remarkable. People, if we repeat the game, people cooperate more often if we repeat the game than if we don't. Now, both of those are deviations from the Nash behavior or the subgame perfect behavior. But it's kind of interesting that there's a larger deviation from Nash if we repeat the game relative to if we just play it one time. I think that just goes to show how strong that incentive on the last day is. And the question is, do people then use the last day properly? So we need to think about what would happen if we repeated this game an infinite number of times, because a finite number of times isn't going to create any cooperation. A finite number of times is just as sad as the one time. No matter how big that finite is, it's just as sad. So what would happen if we repeated this game an infinite amount of time? Now, in order for us to pin that down in the B and the C block, we need to introduce the machinery right now. So the first thing I want to do is I want to introduce the notion of patience. Patience. Or on the flip side, discounting. How much do you discount the future relative to today? A patient person values the future about as much as they value today, and an impatient person cares only about today. So in order to motivate this, suppose that I gave you $100. Don't get your hopes up. Suppose I gave you $100. You're pretty happy. You're whatever your utility of $100 is happy. Maybe that's 100 happiness points. Maybe not. There's diminishing returns on money. Regardless, you have your happiness for $100 today. And you would pay $100 to get $100 today. It's kind of weird sounding, but you would pay $100 to get $100 today. Maybe you make change. But here's a question. How much would you pay today for a contract that I wrote for you that said that you get $100 in a year? And suppose that the contract is credible. Suppose that the question is just basically, how much do you value $100 right now versus $100 in 1 year? Would you pay $100 today for $100 in 1 year? Probably not. Probably not. Would you pay $99? Probably not. But would you pay $0 for a contract worth $100 in 1 year? You'd probably pay more than $0. Of course you'd pay $0 for it. If I offered it to you for free, you'd take it. But if I said, I'll need $1, you give me $1 today, and in 1 year, I'll give you $100. Boy, that's a hell of an investment. It's an investment opportunity of a lifetime. So if I said to you, you give me $1 today, and I give you $100 a year from now, and suppose that's credible, you'd take that deal. Probably. But if you were starving to death, you wouldn't. Right? If you went to the street and found somebody who was hard on their luck and was asking for money and said to them rather cruelly, well, you give me one of those dollars that you've been begging for, and I'll give you 100 in a year, and I promise it'll be true, and suppose that was credible, they still might not take it because they need that dollar today very badly. But if you're in a better situation than that, which be grateful if you are, then chances are good that you would pay $1 today for $100 in a year. Depending on how patient you are, you might be willing to pay more. If you're an immortal, if you're just an immortal being that's going to be here forever, maybe you'd even pay like $90. You might be willing to be very patient and say, $100 in the future is worth $90 to me today. But there's an interesting kind of rescaling. What we're doing is we're taking that money and we're rescaling it. And so what I want to do is show you how you would rescale utils. So suppose that I said to you that a util today was worth more than a util tomorrow. 1 happiness point today was worth more than 1 happiness point tomorrow. The way that I encode that is by introducing a discount term. So if I offered you a happiness point today, that would be worth 1 happiness point. And if I offered you a happiness point tomorrow, in time period 1, that'll be worth delta happiness points, where delta is a number that's greater than or equal to 0 and strictly less than 1. So it's worth less. Delta times that 1 happiness point will be worth less than 1, and potentially more than 0. If you're very impatient, so the delta is 0, then that happiness point tomorrow is worth nothing to you. You only care about today. However, if you care a little bit about that happiness point tomorrow, then maybe delta is greater than 0 and still strictly less than 1. If you're very patient, then delta will be a number very close to 1, so that the happiness point tomorrow is worth almost as much as the happiness point today. What we're doing here is we're just rescaling the utils so that the future is worth less than today. And the idea is that we're going to exploit the fact that delta falls between 0 and 1, and if you square a number between 0 and 1, it gets smaller. So in other words, a happiness point today is worth a happiness point today. A happiness point tomorrow is worth delta times that happiness point, which is smaller. A happiness point in 2 days is delta squared times that happiness point, which is smaller still. 3 days, delta cubed times that happiness point, which is smaller still. And so on. In other words, that happiness point will decay. It will decay. Let me show you what I mean by that. Suppose that I plot time on this axis and happiness points on this axis. And I want to know what's a happiness point worth today, tomorrow, and so on. So here's time period 0, which is today. And a happiness point today is worth delta to the 0 times 1. Delta to the 0 is just 1. So that's 1 happiness point. However, at time period 1, now it's only worth delta happiness points. And depending on where delta is, that comes up a little bit short. Similarly, if at time period 2, we go to delta squared, which is even a little bit lower still. We wind up with this sort of, it's called geometric, right? It's this decay, all right? And eventually that's going to go all the way to 0 if there's a long enough time horizon. It won't go exactly to 0, but it'll start to be very, very tiny infinitesimal happiness points, because you really don't care that much about what's going to happen in a Google years. If delta is a number very close to 1, so that you're very patient, this decays very slowly. If delta equals 0, so that you don't care at all about the future, then in time period 0, it's 0 to the 0th power, which is still 1, times 1 happiness point. And then every other day, it's straight down to 0. It just decays immediately. And in between, you can have sort of patient people decay very slowly, impatient people decay like immediately, and intermediately, they decay sort of with this gentle curve. Okay? So depending on how patient somebody is, we can think about how much they weigh the future, and that has nice visual intuitions. This scaling by the delta is going to help us to overcome the St. Petersburg paradox problem again by allowing us to think about an infinite stream of a happiness point, and it turns out that that won't be worth an infinite amount of happiness. Let me show you what I mean. So the question here is, given some discount term, given how much they discount the future, given some discount term, what is an infinite stream of happiness points worth? I give you a happiness point today. I give you a happiness point tomorrow, ... and no ending. I just keep giving you a happiness point. Every day you wake up, you get a happiness point. You wake up, you get a happiness point. You wake up, you get a happiness point. What's that worth if we're discounting the future? Well, in time period 0, you get delta to the 0 equals 1 times 1. Plus, in time period 1, you get delta to the 1, which is delta, times 1. In time period 2, you get delta squared times 1, which is delta squared. And so on. You get 1 plus delta squared, plus delta cubed, plus delta to the 4, ... Forever. No ending. The idea here is that we don't know when the end of time is. And if we view things that way, then we wind up with this sum. It's an infinite sum. And you can view this as the sum from n equals 0 to infinity of delta to the nth power times that 1 happiness point. That's what an infinite stream of ones would be worth to somebody given some discount term. Notice that if delta is 0, then that's only worth 1 happiness point. You get the 1 happiness point today and the rest I don't give a crap. But if delta is close to 1, so we have a patient person, then that looks like it's going to be a pretty big number. Maybe it's close to infinite. Maybe it is infinite. Maybe we have the St. Petersburg paradox problem again. No, we don't. So before we move on to the B block with the analysis, let me just show you a couple of tricks about what to expect from some of these streams. These tricks, these are going to be magic fairy dust. This is something that you learn in an analysis class, and I'm going to spare you all the agony. So it turns out that this sum, starting from 0 and going to infinity, if you calculated that, that works out to 1 over 1 minus delta. How zany is that? That works out to 1 over 1 minus delta. Notice then that if delta is 0, then that is 1, as promised. That's 1 over 1 minus 0, which is 1 over 1, which is just 1. However, as delta gets bigger, that denominator gets smaller and smaller, and so the happiness number gets bigger and bigger. Right? So if delta is 1/2, then it's 1 over 1 minus 1/2, which is 1/2, which is 2. If delta is 2/3, then it's 1 over 1 minus 2/3, which is 3. The more patient you get, the bigger this number becomes. Right now, those squared and cubed discounted terms are acting like a concave function. They're sort of concavifying what we're working with here so that it doesn't just go to infinity. Again, go back to expected utility week if you want some intuitions. So in other words, the sum from n equals 0 to infinity of delta to the n is 1 over 1 minus delta. We'll use that one pretty often. If I had started at 1, so if I got 0 happiness points at time period 0, and then we just started from 1, then that would be delta over 1 minus delta. There's going to be 6 of these little tricks. We're not going to use them all, but there's going to be 6 tricks. If I started from n equals 2, so if I got 0, and then delta squared plus delta cubed, and so on, then that would be delta squared over 1 minus delta. So those are all pretty intuitive. Now we're going to have occasion to like skip over a number. So suppose that I got like a happiness point in time period 0, nothing in time period 1, a happiness point in time period 2, nothing in time period 3. So in other words, if I got a happiness point just on the even days, then that works out to 1 over 1 minus delta squared. If I only got a happiness point on the odd days, 1, 3, 5, and so on, then that would be worth delta over 1 minus delta squared. And finally, if I started from 2, if I went 2, 4, 6, 8 when I got a happiness point instead of 0, 2, 4, 6, 8, that would be delta squared over 1 minus delta squared. You'll see why we need these over in the B block. All of these little infinite sum tricks, these are things that you use when you think about different possible revenue streams over an infinite time horizon. And every one of those patient terms, if they go to 0, it takes us just to the time period 0 payoff. But as delta gets bigger and bigger, so that we get more and more patient, we get smaller and smaller denominators, and therefore bigger and bigger happiness numbers. So the more patient we are, the more we value these revenue streams, but so long as delta is strictly less than 1, it converges to a number so that we can meaningfully give utility numbers. We can have meaningful utility functions over these infinite revenue streams. That's what we're doing here. We're trying to assign numbers. We're trying to come up with a number that conveys if you prefer one infinite revenue stream over another infinite revenue stream. That's it. How do you value different infinite revenue streams? And this patient term plays a really big role in it. So we now have all our ducks in a row. We've seen that a finitely repeated prisoner's dilemma doesn't buy us anything, and we've talked about how we would try to extend some logic to infinite streams of utility numbers. What if it wasn't finite? What if it was infinite? So over in the B block, we'll have to talk about how we use this apparatus to try to save ourselves from this mutual defection for a finite amount of time. What if we don't know the ending of the story? What's the ending of the endingless story? I'll show you in the B block. See you there. So here in the B block, I want to talk about the infinitely repeated prisoner's dilemma. So what we're going to try to do here is we're going to try to think our way through what would happen if we played the prisoner's dilemma not a finite number of times, but an infinite number of times. We'll have to think about what we mean by a strategy in an infinitely repeated game, and then we'll have to think about what deviations from that strategy would look like. It's kind of a nightmare. Imagine that I had an infinite stream of cooperate. Every day I wake up and I cooperate. What's a deviation from that strategy? There's like so many. We'll see that there's a way to simplify this, and it's going to be more straightforward than you realize, but just be prepared to have your mind bended a little bit, okay? So in order for us to develop a strategy for an infinitely repeated game, we're not going to be able to say what do you do with every decision node because there's too many decision nodes. We don't know what every decision node looks like. We don't know. I can't say to you at decision node 39, do this because there's so many decision nodes. I can't come up with a list of all the decision nodes. Instead, what we need to do is we need to develop a kind of strategy that lets us know what to do as a default setting and then sort of conditions what to do in future interactions based on what we've seen today. It's going to wind up looking an awful lot like a computer program where there's an initial state and then a bunch of if-thens. A bunch of if-thens. That's what a strategy is in an infinitely repeated game, is an initial state and what to do in all the future states. It's actually a little bit more straightforward than it looks, and it gets kind of fun if you let it, but, you know, that's a weird person telling you that. I think by way of example, it'll be easiest for us to just look at one strategy and then use it for an equilibrium analysis, okay? So I want to introduce a strategy called Grim Trigger. A lot of these strategies have very fancy sounding names for the record. I want to talk to you about what a Grim Trigger strategy is in the infinitely repeated prisoner's dilemma. It's a way to encode a particular kind of story. Suppose that I am a nice person, suppose. And I am the sort of person that as a default setting, I'm willing to say I'm going to cooperate. My baseline setting, my default setting is to cooperate. I'm a cooperator. We wake up today and I am prepared to cooperate. But I hold grudges. I hold very long grudges. I hold for the rest of time grudges. I'm the sort of person that so long as you've been nice to me, I'll keep being nice. But if you're ever mean to me, I will be mean to you back for the rest of time. I will punish you. I'll put you in the penalty box. So how would we encode that? How would we encode that strategy? Well, it's going to look like a computer program. So if I'm dialing up Grim Trigger. So, point 1, as an initial setting, cooperate. Cooperate. Your initial setting, time period 0, you will cooperate. Now we need to think about the ifs. So in Grim Trigger, it's relatively straightforward. If either player has ever deviated in a previous time period, then defect. If you've cooperated, if you've defected in any previous time period, or if I have too, if either of us has ever defected in previous time, then you should then the strategy says defect. And if nobody has ever defected in previous play, keep cooperating. There's 3 things here. In time period 0, you cooperate. In future time periods, if anybody has ever defected, you defect. You do the nasty thing. And in future time periods, if nobody has ever defected, you keep on cooperating. That's Grim Trigger. So an interesting question is, if I was playing Grim Trigger and you were playing Grim Trigger, then what would be the streams of utils? What would be the streams of utility numbers? Right? So if you're playing Grim Trigger and I'm playing Grim Trigger, on time period 0, in time period 0, I cooperate, you cooperate, 1 happiness point apiece. In time period 1, we both observe that neither of us has ever defected, therefore we both cooperate, 1 happiness point. In time period 2, we both observe that neither of us defected in time period 0 and neither of us defected in time period 1, we both cooperate, 1 happiness point. In time period 3, we both observe that neither of us defected in periods 0, 1, or 2, therefore we both cooperate. In other words, if we both play Grim Trigger, if we're both playing Grim Trigger, then we just get a steady stream of 1s every day for the rest of time. And let's assume that we both have a discount term, and we'll just have it be the same discount term. We're equally patient. And so we set delta equal somewhere between 0, it could be equal to 0, and 1, it's got to be strictly less than 1, because we don't value the future exactly as much as today. So in other words, my utility for playing Grim Trigger against you playing Grim Trigger is 1 over 1 minus delta. And your utility for playing Grim Trigger against Grim Trigger is 1 over 1 minus delta. So those are our utilities for playing Grim Trigger. Now, an interesting question is, does either of us want to deviate? Because if neither of us wants to deviate, then that's an equilibrium. But there's so many possible deviations. There's a million possible deviations. There's more than a million. There's so many deviations that it's hard to keep track of, right? It could be that I defect in one of the time periods, or I defect in some two of them, or in some three of them. And you don't know. It could be time period 1, 2, and 3, but it could be time period 1,032, 10,976,222, and 9,477,777,000, right? I defect in those three, or any 4, or any 5. There's so many possible deviations. It could be, there's all these possible deviations from Grim Trigger. So the question becomes, how do we study that? Because that just sounds like too much. I'm going to show you one of the coolest tricks in all of dynamic optimization. In fact, it's the coolest trick in dynamic optimization. It's called the one-shot deviation principle. So in the context of this game, what the one-shot deviation principle means is that something will be in equilibrium. A strategy against another strategy will be in equilibrium if and only if there's no incentive to deviate in one time period and then revert back. So instead of having to study all these possible deviations, all the 1s, all the 2s, all the 3s, all the 4s, that's actually bigger than an uncountably infinite number, right? That I think we need to go to Aleph 2 for that. I could be wrong off the top of my head. Instead of having to worry about all these possible deviations, all we have to think about is a deviation at a given time period conditional on every possible sort of input for that. You'll see what I mean here in a second. So the idea here is there'll be a deviation time, which we'll call time 0, just to make our lives easy. And the idea is at time period -1, whatever was before the possible deviation day, we'll have to think about, well, what if the time prior we were both cooperating? What if the time prior we were both defecting? Or what if it was a CD or a DC? So I've got my one table of what happens if neither of us deviates, if we're both playing Grim Trigger against Grim Trigger. And down here, I'm going to put what happens if player 1 deviates at time period 0. And the idea here is we're going to say that time period 0 is the special day where I potentially deviate. And we'll see if I have a profitable deviation. Do I have a profitable deviation by doing the anti-Grim Trigger thing at time period 0? Now suppose that at time period -1, we were both cooperating. Then time period 0, I wake up and I have a bad day and I don't do the thing that I'm prescribed to do by Grim Trigger. Instead, I do the non-Grim Trigger thing of defecting, right? Now you're playing Grim Trigger. You're still playing Grim Trigger, which means that you cooperate, which means that at time period 0, I get 2 happiness points and you get -1. I'm like, I'll take that short-term goodie. Instead of taking 1 happiness point at time period 0, I'll take 2 instead, on the understanding that this could turn south in the future. What do I mean? Well, if I revert to Grim Trigger and you continue to play Grim Trigger, then that means that in time period 1, you defect and I defect. We both defect and we go to 0 happiness points. Time period 2, we keep defecting. Time period 3, we keep defecting. My one-shot deviation at time period 0 turns what had been an infinite stream of cooperation to an infinite stream of defection. Now the question is, this is where patience comes in. The question is, does that 1 extra happiness point that I get for doing the nasty thing at time period 0 outweigh what I have to put up with, which is an infinite stream of 0s instead of an infinite stream of 1s? Well, in order to work that out, let's think about what my utility is for deviating. Well, I get 2 happiness points at time period 0, so that's 2 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 equals 2. So my utility for deviating from if our history was CC, my utility for deviating is 2. Well, when is 1 over 1 minus delta for playing Grim Trigger better than 2 for that one-shot deviation? Well, if delta is greater than or equal to 1/2. If delta is greater than or equal to 1/2, then I value all those 1s more than the extra happiness point that I get at time period 0. So let's just work on the assumption that delta is greater than or equal to 1/2, because as of right now, I don't want to deviate, assuming CC was my input. What if CD was my input? What if at time period -1, the hypothetical time period -1, I cooperated and you defected? Well, we're both playing Grim Trigger, which means that in time period 0, you've observed a defection, so you'll defect too. But I'm going to deviate. I'm not going to do the Grim Trigger thing because I woke up this one day and I say, I'm not going to do the Grim Trigger thing. Instead, I cooperate again. So that means I get -1 happiness points. And then I revert back to Grim Trigger. It was a one-shot deviation from Grim Trigger, so I revert to my infinite punishment and I get a steady stream of zeros because you're defecting too. So in other words, if it was CD as the input, I one-shot deviated by cooperating on this one weird day, and then I go back to playing Grim Trigger, my utility is -1 happiness points, which is always worse than 1/1 minus delta. So I don't want to deviate from Grim Trigger if the input was CD. What if it was DC? What if on time period -1, I defected and you cooperated? Well, at time period 0, you're going to defect because you're playing Grim Trigger the whole time. But I'm going to cooperate just as a form of deviation. And that again takes me to -1 at time period 0, and then an infinite stream of zeros. I get -1 happiness points. I don't want to deviate. Finally, if it was defect as an input, well then, if I'm supposed to be defecting in time period 0, you're defecting in time period 0, I have this one-shot deviation day, and I cooperate, I get -1 happiness points, and then I get a steady stream of zeros again. So in other words, I don't want to deviate because I get that -1 happiness points. In other words, Grim Trigger is a best response to Grim Trigger so long as I'm sufficiently patient, so long as delta is greater than or equal to 1/2. So if my delta is greater than or equal to 1/2 and your delta is greater than or equal to 1/2, or if we both have the same delta and it's greater than or equal to 1/2, Grim Trigger is the best response to Grim Trigger, is the best response to Grim Trigger, is the best response to Grim Trigger, is the best response to Grim Trigger. Grim Trigger versus Grim Trigger is a subgame perfect equilibrium. Now let's think about that. That means that on day 0 we cooperate, and on day 1 we cooperate, and on day 2 we cooperate. We cooperate for the rest of time. If we're patient, if we're sufficiently patient, if delta is greater than or equal to 1/2 so that we don't want to grab that goodie, we don't want to defect on that one-shot deviation. If we're patient enough to value the stream of ones more than the stream of zeros, if we're patient enough, then with an infinite time horizon, we will cooperate. We have just made cooperation happen. We have just made cooperation and equilibrium in the prisoner's dilemma. In the saddest of all the stories. In a story so sad that in one shot it's sad, and in any finite number of shots it's still sad. If we view this where we don't know when the last day is, if we don't know when the final nasty will be, and we're sufficiently patient, we'll cooperate. We've saved ourselves. We will cooperate. We have just incentivized mutual cooperation. How? With the nastiest punishment strategy of all time. If you ever make a mistake, I will punish you forever. But that's credible. That's a credible threat. That's a credible enough threat against a patient enough opponent that we will see cooperation. Grim Trigger versus Grim Trigger. Subgame perfect equilibrium. Why? Because of this one-shot deviation analysis. That's pretty cool, right? I mean, it's kind of tragic that you have to have this really nasty threat out there, but it's a credible threat. It's a credible threat. It's credible enough that it makes people cooperate today. The infinite punishment strategy of Grim Trigger. Well, let's think about the other extreme. What if it's a punishment strategy, but it's a punishment strategy where you forgive somebody after you put them in jail for a day? You say, I'm going to defect tomorrow, and then I'm going to go back to being nice, okay? I'm going to defect tomorrow, but I'm going to go back to being nice. That sounds reasonable. That's like the other extreme of a punishment strategy, right? So there's a name for that strategy. It's called tit-for-tat. So the tit-for-tat program, the tit-for-tat strategy goes like this. As an initial state, cooperate. Be nice on the first day. Wake up and do something nice. If either party defected in the previous time period, right? So it's just like if you were nasty yesterday, then defect that day. And then revert to cooperation. So defect for one day and then revert back to cooperation. So in other words, if you defected yesterday, then I'll defect today and I'll go back to cooperating tomorrow. Right? So I forgive you. I punish you for 1 day and then we go back to normal. Otherwise, keep cooperating. If you cooperated last time period, I'll cooperate next time period. Right? So it's basically, if Grim Trigger, instead of having an infinite punishment, it's a one-term punishment. It's a one-time point punishment. Now we're going to have to think about this a little bit more carefully because the top one will be influenced. If we're both cooperating, which is what happens as an initial equilibrium state, so if we're both cooperating, then if we're playing tit for tat, if we're both cooperating on day -1, then I get 1, 1, 1, 1, 1, 1, 1, and you get 1, 1, 1, 1, 1, 1, 1. We get 1 over 1 minus delta. So if we begin from a cooperate, we get 1 over 1 minus delta. Now let's think about what it would mean if I deviated from tit for tat if we were both cooperating. Well, if that's the case, then we're both cooperating, which means I should be cooperating on time period 0, but I don't. Suppose I do the nasty thing of defecting in time period 0. I have a one-shot deviation. If I had a one-shot deviation and I reverted back to tit for tat, now this is going to get weird. Think about this. So that means in time period 0, I defect and you cooperate. You didn't deviate. Which means in the next time period, I go back to playing tit for tat. Did you deviate in time period 0? No, so I cooperate. Did I? Yes. And you're playing tit for tat, so you defect. So in other words, if it's DC in time period 0, then it's CD in time period 1. And then it's DC in time period 0, in time period 2. And then it's CD again in time period 3, and so on, ... We just have this chain, DC, CD, DC, CD, DC, CD. We just have this little infinite stream of snark. We're just snarking. I punish you, I punish you, I punish you, I punish you, I forgive you, I forgive you, I forgive you, I forgive you. It's like watching Selling Sunset. Now let's think about what that's worth. Well, in time period 0, I got 2 happiness points for that defection. In time period 1, I get -1. In time period 2, I get 2 again. In time period 3, I get -1. It's almost like that odds and evens things were there for a reason. The deviation utility, if you use those tricks that I showed you in the A block, that works out to 2 minus delta over 1 minus delta squared. 2 minus delta over 1 minus delta squared. So my utility for a one-shot deviation from tit for tat when the input was CC is 2 minus delta over 1 minus delta squared. And my utility for playing tit for tat was 1 over 1 minus delta. So when do I not want to deviate from tit for tat? So there we need delta to be less than or equal to 1/2. We need you to be sufficiently impatient. So we need you to be sufficiently impatient. We need delta to be less than or equal to 1/2. If delta is less than or equal to 1/2, then I don't want to deviate. That 1 over 1 minus delta is better than 2 minus delta over 1 minus delta squared. So if I'm sufficiently impatient, I won't deviate. Because if I'm patient, then maybe I care about all those 2s. I care about all those 2s. I'm getting 2s versus -1s. I'm getting big benefits and little punishments. So if I'm patient, then I'll take that 2 and -1 chain. If I'm impatient, I'll just take all the 1s. So that's if my input was CC. If my input was CD, let's say I was cooperating and you were defecting in time period -1. Well then, my tit for tat thing to do would be to defect, and you're still playing tit for tat, so you would cooperate. So I would get 2 happiness points in time period 0, -1 in time period 1, 2 in time period 2. In other words, my utility for playing tit for tat against you playing tit for tat, if the input was CD, is 2 minus delta over 1 minus delta squared. If I deviated and you were still playing tit for tat, then from CD, I should defect, but I'm going to cooperate because I just wake up one day and I feel suddenly very nice, apparently. And we wind up with a cooperate in time period 0, which is worth 1 happiness point. And I just get a steady stream of 1s after that because now my one-shot deviation has turned to super nice. Now we're just cooperating all the time and getting 1 happiness point all the time. So it's 1 over 1 minus delta. Well, that's the exact, now we need it to be the case that delta is greater than or equal to 1/2 because this is the same exact inequality, but in reverse. So I need to be sufficiently patient in order for this not to be a profitable deviation, which means now I need delta to be exactly equal to 1/2 because in order to not deviate from CC, I needed it to be delta less than or equal to 1/2. In order to not deviate from CD, I need it to be delta less than or equal to 1/2. Those are both true only when delta is exactly equal to 1/2. Delta is exactly equal to 1/2. Now we need to think about if it was DC as the input. Well, if it's DC is the input and I'm playing tit for tat against you playing tit for tat, then it should be that I cooperate and you defect. So I get -1 today and you get 2 today. And then I get 2 and you get -1, and so on. Right? That turns into a -1 then 2, then -1 then 2, then -1 then 2. If you use the tricks from the A block again, the utility of playing tit for tat against tit for tat when DC is the input is 2 delta -1 over 1 minus delta squared. Now let's suppose that I deviated instead. So if I deviated, then what would happen is, starting from DC, I know you're going to defect, and then I would defect. So instead of cooperating like I should playing tit for tat, now I defect and we both get 0 happiness points. And then the next time period, you defect and I defect. And that it's just a steady stream of zeros. So you get 0 happiness points. You get 0 happiness points for the rest of the time. Right? If I woke up and then I suddenly defected when I should have cooperated, then we just kind of keep defecting forever. There isn't a profitable deviation so long as delta is greater than or equal to 1/2, which means delta equals to 1/2 because we've already ruled out all the ones where it's strictly greater than, right? So as of right now, tit for tat is still reasonable against tit for tat so long as delta is exactly equal to 1/2. The last thing we need to check is what happens if the input is DD. So if the input is DD, so that means that we should both be defecting in time period 0. We should both be defecting in time period 1. We should both be defecting in time period 2, and so on. Steady stream of zeros. So playing tit for tat against tit for tat when the input is we both defected is a steady stream of zeros. The utility of that is 0. Well, what if I woke up and I suddenly deviated? That means that you keep defecting because you didn't deviate, and I suddenly wake up and I start cooperating. So I get -1 happiness points today. That sounds stupid. Then the next time period, I go back to tit for tat, and you keep playing tit for tat. You now forgive me. So now the next time period, I defect and you cooperate, and then I get 2, and so on. It's a steady stream of 2s and -1s and 2s and -1s. That works out to 2 minus delta over 1 minus delta squared. That's actually the same exact comparison as the last time, but in reverse. So there we would need delta less than or equal to 1/2, which again requires delta to be equal to 1/2. So if delta is exactly equal to 1/2, then tit for tat is a subgame perfect equilibrium against tit for tat. So just notice one thing with me. If we imagine delta here on this axis, the set of deltas where Grim Trigger is a subgame perfect equilibrium against Grim Trigger is everything that ranges from delta equals 1/2 all the way up to delta equals 1. So if we're willing to punish for an infinite amount of time, we can any one of these patience terms would allow that infinite punishment strategy to be in equilibrium against itself. However, if we're punishing only for one time period, then we need delta to be exactly equal to 1/2. And as we have intermediate amounts of punishment, we can have intermediate amounts of patience that we can use to support that intermediate amount of punishment. So in other words, tit for tat is just a limiting case of Grim Trigger, and Grim Trigger is just a limiting case for tit for tat, where Grim Trigger allows us to micro-found cooperation for many kinds of patience, tit for tat for a particular kind of patience, and in-between punishment strategies for in-between patience. So that's kind of interesting when you think about it, but regardless, what we've done is found ways to incentivize cooperation in a game that seemed uncooperatable. We have saved ourselves from ourselves by thinking about the future and saying, I will punish you. I announce that I will punish you for some amount of time. And you say the same to me, and that threat of punishment, so long as we have the right amount of patience, might be enough to micro-found good behavior. I say might for a reason. Over in the C block, I'll show you just how many possibilities there are. It promises to be a bit of a mind twister, as opposed to this block. Well, you'll see when we get there. Multiply by delta, and I'll see you there. So here in the C block, I just want to show you a quick folk theorem. So in order for me to get the most out of this folk theorem, I want to introduce the concept of a min-max. It's like the worst that I can do when I'm best responding to you. right? It is my worst best response. Let's just look at the prisoner's dilemma again. What is my min-max? What is the worst that I can get for best responding? So if you're cooperating, then the best that I can do is defect and get 2 happiness points. So if my best response gets me 2 happiness points. Conversely, if you're defecting, my best response gets me 0 happiness points. My min-max value of this game is 0 happiness points. That is the worst that I can do among the things that are best responses. That's my lowest happiness number among things that get a star. The question is, what is my worst thing, depending on what you're doing, across all the things you could be doing when I'm best responding? God, that's an awful sentence. So a min-max payoff is the minimum of all of your possible strategies, of the maximum of all of my possible strategies, of the utility for your strategy and my strategy. What is the worst best thing? In the prisoner's dilemma, my min-max payoff is 0 and your min-max payoff is 0. Let's just to keep things spicy, let's think about the stag hunt instead. So remember in the stag hunt, stag, hare, 2, 2, 1, 1, 0, 1, and 1, 0. So if you're hunting for stag, the best thing I can do is get myself 2 happiness points. And if you're hunting for hare, the best thing I can do is get myself 1 happiness point. The min-max payoff in stag hunt is 1. I would advise you to go find the min-max payoff for all the games that we've discussed over in the games lecture. It's not that hard. You'll see. It's really not that hard. So it's with that fresh in mind that I want to draw a particular picture, sort of carve it up using the min-maxes, and then give you a result. Okay, so let's start from a utility imputation space. So what I want to do is I want to have a utility imputation space. I will put the row player's utilities here and the column player's utilities here. Notice that I'm going to treat these as if we're doing a one-shot game, and I'm going to do this by multiplying all these revenue streams by 1 minus delta, which just takes us back to the same units as a one-shot version of the game. So when I plot this here with 2 and minus 1 and 0, 0, that's not the same thing as 1 over 1 minus delta. But if I multiply that by 1 minus delta, then I wind up with that 1 happiness point. So 1 over 1 minus delta, if I normalize it by just saying, let's just put all in the same units, that gets me to the 1, 1 point, just as before. Now let's think about the payoffs for our modified version of the prisoner's dilemma. If we both cooperate, that's 1 happiness point apiece. If I cooperate and you defect, minus 1 for me, 2 for you. Same in reverse, if I defect and you cooperate, 2 for me and minus 1 for you. And if we both defect, 0 happiness points apiece. The first thing I want to do is I want to take these 4 dots and I want to draw lines between them all. And I want to fill in everything in between. This is the fancy term for this, is it's called the convex hull. This is just the set of all possible combinations of these 4, all possible linear combinations of these 4 dots, right? So it covers 0, 0, it covers 1, 1, but it covers everything in between them. And it covers every mix of those 2 things and 2 minus 1, and so on. What this is every possible utility combination that falls in between the 4 possible utility combinations of pure strategies. So for example, 1/2, 1/2 is in this, but 3/2, 3/2 is not. So I've got this sort of funky diamond. I've got this funky diamond. And I'm gonna begin from this funky diamond. Now I want to carve up my funky diamond. And I want to do that by saying that I only want to focus on utility imputations that are greater than the min-max payoff of 0. So what I'm going to do is I'm going to carve off everything worse than the min-max payoffs. So what I want to do is I want to chop off every part of the funky diamond where player 2's utility is lower than 0. That's this little triangle part. And I'll do the same for player 1. I'll chop off this little diamond, this little triangle from the funky diamond. What I'm left with is this very funky shape where the bottom corner is 0, 0. There's a top at 1, 1, and then there's sort of like this weird frontier that's been truncated. And you're like, what the hell is this shape? What this is the set of all possible normalized utility imputations, the value of all possible infinite streams, such that it's feasible, it could actually be achieved for some set of strategies. It doesn't like take us to 3/2, 3/2. and it's at least as good as the min-max for all players. So this very funky shape is just all the feasible payoff vectors that are at least as good as your min-max. There's an uncountably infinite number of utility payoffs in here, right? So 1/2 is in here. 3/4 is in here. 3/4 1/4 is in here. There's all sorts of payoffs in here. There's an uncountably infinite number of utility imputations living in this set. Now here's the thing I want to tell you. This is really funky. Choose any pair of utilities out of this set. Any pair of utilities. Fair, unfair. 1-1, 0-0. Wasteful, not wasteful. Choose any pair of utilities out of this giant set of utility imputations. Choose any pair. Any pair of utilities. Any vector at any point in this funky shape. So here's the result. This is the Folk theorem. You choose anything that's at least as good as min-max and feasible. Then there exists some special delta, call it delta overbar, some amount of patience, such that for any delta bigger than that cut point, there exists a subgame perfect equilibrium that generates that exact utility imputation. Let that sink in for a second. Write that down if you need to. But here's what it means. If you give me any desired utility outcome that's feasible and better than the min-max, if it's feasible and better than min-max, and sufficiently patient players, I can generate strategies that give you that exact payoff as a subgame perfect equilibrium payoff. So if you wanted to get 1-1, you just do Grim Trigger or tit-for-tat. If you wanted to generate 0-0, well, anything would generate 0-0 because it's a subgame perfect equilibrium no matter the delta for them to defect forever. But if you wanted to generate exactly 1/2 as the outcome, you could do it with sufficiently patient players. Or something really close to 1/2. You could do it with sufficiently patient players. Or something really close but just worse than 1-1. Or something Pareto optimal and close to 1-1 but slightly in favor of player 1 instead of player 2. No matter which of this giant set of utility combinations you choose, with sufficiently patient players, you can design a punishment mechanism or an incentive mechanism. You can come up with an institution. You can come up with rules. You can come up with laws. You can come up with how long will I punish you for any given sin. You can come up with an institution that generates that outcome. No matter what, for every one of these, you can come up with the right strategy to do it. You can come up with the right Grim Trigger or tit-for-tat or something else. There's a program that you could write that would generate that outcome if you had sufficiently patient players. If they're impatient, you're going to get 0-0 no matter what. But if you have sufficiently patient players, where for every possible combination, there's a cut point, a different cut point, you can make that happen. Think about what that means. It means that you can come up with the appropriate sentence lengths, or the appropriate penalty box lengths, or the appropriate carrots, the appropriate amount of incentives. You can always come up, no matter what outcome you would like to generate in terms of the utilities, you can generate it. Sufficiently patient. And that means that you could get the 1-1 if you wanted it, but you could also come up with any Pareto optimal outcome that's at least as good as min-max, basically a bargaining range kind of thing. You could generate a strategy, you could generate a program that comes up with any Pareto optimal outcome or Pareto non-optimal outcome. No matter what you want out of this giant set in this funky diamond, you can get it. That's the Folk theorem. That's the Folk theorem for infinitely repeated games, in particular when we're thinking about the infinitely repeated prisoner's dilemma. It's a massive set of outcomes that can be generated. Now, what does that mean? It means if you're clever, under anarchy, you can manipulate things if you want to. We could generate any outcome we wanted to organically. Or ideally, you'd tell people what their strategies were going to be so it was common knowledge, and then they would just play as prescribed. That's essentially what bylaws do. That's essentially what rules are these programs, these strategies, and these infinite games. So what the Folk theorem tells us is there's an infinite amount of possibilities, a massive amount of possibilities, depending on which institution you write down. So this utility imputation thing that just seems so fatalistic, it seems like, well, there's a Nash equilibrium and that takes us to one of these utility imputations. And that allows you to do waste and fairness analysis, or allows you to do Pareto analysis, or whatever. What I'm saying to you is, once we get to infinite, then we are the controllers. We're not reacting to where the equilibria take us. We're saying, I can design an equilibrium that gets me there. Suddenly, we're not reacting to the game. We're designing with the desired outcome. That's kind of cool when you think about it, right? And I know that's really hard, but it's a little bit of a mind bender. But if you view it not as something where like the game is out there and then we respond, but rather the game is out there and now we design programs to work around the game, to try to use the infinite repetition of the game. Suddenly this becomes a world of possibilities rather than the world of constraints. Even though we're completely rational, completely credible, very subgame perfect, all the things we've talked about, even with all of that, and in fact, because of all that, there's possibilities rather than constraints. Fascinating when you think about it, right? Well, I have a lot of faith that if you can draw this picture at a dinner party, people will be talking about you for years to come. You will be the sensation of the season. So start practicing drawing this on a cocktail napkin. You can come up and try it with me if you want to. That's the whole point of a whiteboard. It's just a giant cocktail napkin that you can erase. Talk about today? Well, in contrast with a lot of our lectures lately where it's been like, let me show you all these things and then here's what happens. Now it's been like, let me show you one thing and let's just squeeze all we can out of it. And in fact, we saw in the C block that there's an awful lot to squeeze, more than we could ever hope to squeeze. But along the way, we also learned that if we take a very sad story like the prisoner's dilemma, and in fact, a very sad story like the finitely repeated prisoner's dilemma, which in a sense is sadder, right? And if we're clever, if we use patience, if we use these infinite streams, if we're willing to think about no end of days, if we're willing to think about what happens if you don't know when the end of time is, if we're willing to do that, then suddenly we can take this nasty story, this sad story, this thing that has puzzled philosophers for a very long time, and suddenly incentivize cooperation in an equilibrium, rational, sequentially rational, credible, subgame perfect kind of way. We can take what had been a very sad story and turn it happy if we have sufficiently patient players who are willing to engage in very long punishments. I mean, these players are willing to subject themselves to very long punishments, potentially. And that's the way of locking in. That's the way of saying, okay, you can punish me forever because I'm patient enough to cooperate. Go ahead, I don't care. I have nothing to hide. You can promise to punish me for the rest of time and I really don't care because I'm not planning on defecting. I'm patient enough that steady stream of ones is worth it to me. This notion of patience is underneath a lot of things that aren't just game theory, right? So when you think about interest rates, this is a way of capturing how patient people would be. If I give you some money so I can't use it today, how much will you have to give me in the future? Right? If interest rates were negative, then that wouldn't be so great because what you'd be saying is I'll give you some money now and you can give me less later. Turns out that natural savings rates might screw some of that up, but I'm not a macroeconomist. So if I'm really patient, then I don't need an awful lot of interest rate because that $1.10 that I get from my dollar, it's okay to me. But if I'm pretty impatient, I'm going to need an awful lot of money in the future in order for me to give you some today. Now, with savings accounts and interest rates in there, this is pretty constant, but you'll see eventually when it comes time for you to decide between your stocks and your bonds, and indeed which bonds you want to buy, you'll see that the credibility of payoff combined with the patience of bond investors who are sometimes a little bit strange, you'll see that there are some perverse things that happen, and consequently, companies might have to give you an awful lot of money over time to compensate for your money today, particularly in the case of junk bonds, which aren't very credible. But your retirement account notwithstanding, there's the big lesson to learn here where infinite streams can incentivize good behavior today and tomorrow and tomorrow and tomorrow. Somebody call Macbeth. You know, now that we've concluded our introductory analysis of time, it's a time to stop and reflect. We've introduced time in easy and hard ways, and we've seen that it really enriches the analysis quite a bit. It takes what had been sort of this static, steady state sort of thing, and then turns it into a what would you do, what would you do, what would you do? And that seems realistic in a lot of ways. But there's a lot of situations that are still simultaneous. You know, when the shepherds decide what to do today, the story is perfectly good today, even if it's interesting to think about what it would look like for an infinite stream of days with shepherds. But you might be thinking that this end of time thing, this fact that there is no end of days, seems pretty unrealistic. You might be thinking, well, I know about entropy and I know that the sun's going to give out here eventually. And yeah, it might be infinite, but you don't have an infinite. You only have a couple billion years to work with. And a couple billion years is still finite. And you might be thinking, okay, but I saved the prisoner's dilemma. That's great, but in order to do so, I had to stop physics. That's not so great. And you're right about that, but you're also not fully right. And it's with that tension in mind that I'd like to conclude with a provocative thought. Physical time and strategic time are not the same time. Physical time, the time that we're experiencing in space-time, I don't want to think about that. That goes way over my head. But the time that we experience in a naive sense is not the same as strategic time. First of all, a unit of strategic time doesn't have to be the same throughout. It matters about what got to be observed. You know, which are the days that are in the future enough that what happens today is observable then? Whereas with the time that we're experiencing, it's hard to know exactly what that would be. It's hard to break the time that we're experiencing into chunks. And certainly it's hard to imagine the time that we're experiencing going on without any end, because for the reasons just mentioned, eventually the universe will stop expanding, or eventually or all of these things, that we will just get to the point where there is no more things happen in the universe, which means there's no more choices made. Because there will be nobody alive. There won't be any atoms that are still working. So those are two important differences between strategic and physical time. I don't mind taking strategic time forever because it isn't really going on forever. It's going on as if forever because we don't know the last day. We don't know when the last possible observation will be. And in order for us to do that, as an act of humility rather than of hubris, we have to say, there's no way the analyst could know what the last day is. And the only humble thing for the analyst to do, a la McCloskey, the only humble thing for the analyst to do is to say, I don't know when the end of days is, and so I just keep going. Because if I knew when the end of day is, I'd make a really sharp prediction of the usual type. But that would require the arrogance of saying that you knew when the last day was going to be. However, there's another workaround that's interesting and worth talking about in the name of encouraging you to be flexible and nimble. Suppose that patience wasn't really patience. Suppose that patience was actually the probability that you thought that tomorrow would be the last day. Suppose that instead of saying that 0.8 is how much you discount the future by, one happiness point today is worth 0.8 happiness points tomorrow. Suppose that 0.8 was the probability that you thought tomorrow was the very last day. And we wouldn't be playing anymore, and there'd be a steady stream of zeros after that. There'd be zeros and zeros and zeros, not because we're playing some game that gives us zeros, but rather because we stopped playing. And it turns out that sort of the last day interpretation of delta generates the exact same outcome as the patience interpretation of delta. So delta isn't just a measure of how patient you are, but also of how humble you are that the interaction is going to end. So in other words, we can think about strategic time going on forever, and then we think about our strategic players and how patient they are. Or we can think about strategic time as ending someday that we don't know, and our players have some sense about when that might be. One is more humble than the other, but they end up giving you the equivalent result. It's easier for me to talk to you about patience than it is for me to talk to you about the probability of breakdown. But once I say it like that, in the context of this hubris versus humility argument, once I mention it that way, then it kind of makes sense-ish. In other words, we might model in a way that seems very arrogant, but that is itself humble because we don't want to announce when the last day is. But that sort of arrogant-seeming model actually has a cousin in the set of humble models where there is a last day, but nobody quite knows when it is. They only have probabilistic expectations of that. It's kind of interesting, not as a matter about the players in our models, but rather about our relationship with them. Do we want to equip them with infinite time and then force them to be patient? Or do we want to equip them with finite time, but where we're humble enough to say that we don't really know when the last day is? And then watch to see what they do, even if they're perfectly patient. In other words, we have a partnership with the players in our models. One of us has got to be limited in one way or another. Either we have to be humble or they have to be patient. Either way, there's a symbiotic relationship between us and the players in our models, which I think is just even more evidence of this being an important tool for introspection. Not as what would you do if you were the player, but rather what do you do as the analyst as you try to understand yourself as the player. This tool for introspection is somewhat epistemological, therefore. It isn't just a matter of what would you do in politics, but rather what do you do in time and space and how do you see yourself there? This got provocative in a hurry. Now, thankfully, this mind bending isn't something that you'll have to think about all that often. But again, I hope that you'll use it as food for thought. What do you think you could possibly know about yourself in an infinite revenue stream? What do you think you could possibly know about yourself when you're patient? And what do you think you could possibly know about yourself when you're perfectly impatient, but you expect time to end eventually? Which is probably how you see things, right? You don't know when your last day is going to be, but you know it's coming. You just happen to have probabilistic expectations about that. I hope that doesn't happen for a very long time, for the record, so please stop smoking. Regardless, this tool for introspection that we've been developing together just keeps getting more and more wrinkled, more and more nuanced. We keep tying ourselves into harder and harder knots, and we can't untie ourselves. I hope you don't. Just continue to realize that there's an important balance to be struck between you, the thinker, and you, the player. You, the abstract, and you, the real. You, the rational, and you, the not so rational. There's all sorts of yous, and the question is, what are you going to do when you get there? I hope you've thought about that in advance so that you know what your program is going to say. Regardless, we've got a little bit more work to do. We've got a little bit more rationality to work through. We have more mountains to climb together on a problem set in class. I'm looking forward to going through this very short time horizon future with you, but I'm also looking forward to seeing what comes up next for you, even if you don't know when the end of time is going to be. Regardless, you finally made it to the end of this particularly arduous moment of time, and for that I congratulate you. And more importantly, I thank you for watching.